In probability theory and statistics, the generalized extreme value distribution is a family of continuous probability distributions developed within extreme value theory to combine the Gumbel, Fréchet and Weibull families, also known as type I, II and III extreme value distributions. By the extreme value theorem, the GEV distribution is the only possible limit distribution of properly normalized maxima of a sequence of independent and identically distributed random variables. Note that a limit distribution need not exist, this requires regularity conditions on the tail of the distribution. Despite this, the GEV distribution is often used as an approximation to model the maxima of long sequences of random variables. In some fields of application, the generalized extreme value distribution is known as the Fréchet-Tippett distribution, named after R. A. Fréchet and L. H. C. Tippett, who recognized three function forms outlined below. However, usage of this name is sometimes restricted to mean the special case of the Gumbel distribution. Specification: the generalized extreme value distribution has cumulative distribution function. 4. Where is the location parameter, the scale parameter and the shape parameter? Thus for, the expression just given for the cumulative distribution function is valid for, while for it is valid for. In the first case, at the lower end point it equals 0. In the second case, at the upper end point, it equals 1. For the expression just given for the cumulative distribution function is formally undefined and is replaced by the result obtained by taking the limit as, without any restriction on x. The density function is, consequently. Again, for in the case, and for in the case. The density is 0 outside of the relevant range. In the case, the density is positive on the whole real line and equal to. Summary statistics: some simple statistics of the distribution are: the skewness is for I3/4 0. For I3/4 0, the sign of the numerator is reversed. The excess kurtosis is where k equals 1, 2, 3, 4, and is the gamma function. Link to Fréchet, Weibull and Gumbel families. The shape parameter governs the tail behavior of the distribution. The subfamilies defined by, and correspond, respectively, to the Gumbel, Fréchet and Weibull families, whose cumulative distribution functions are displayed below. Gumbel or type I extreme value distribution. Fréchet or type II extreme value distribution, if. Reversed Weibull or type III extreme value distribution, if. Where. Remark I. The theory here relates to maxima, and the distribution being discussed is an extreme value distribution for maxima. A generalized extreme value distribution for minima can be obtained, for example by substituting for x in the distribution function, and subtracting from 1, this yields a separate family of distributions. Remark 2. The ordinary Weibull distribution arises in reliability applications and is obtained from the distribution here by using the variable, which gives a strictly positive support, in contrast to the use in the extreme value theory here. This arises because the Weibull distribution is used in cases that deal with the minimum rather than the maximum. The distribution here has an addition parameter compared to the usual form of the Weibull distribution and, in addition, is reversed so that the distribution has an upper bound rather than a lower bound. Importantly, in applications of the GEV, the upper bound is unknown and so must be estimated, while when applying the Weibull distribution the lower bound is known to be 0. Remark 3. Note the differences in the ranges of interest for the three extreme value distributions. Gumbel is unlimited, Fréchet has a lower limit, while the reversed Weibull has an upper limit. One can link the type I to types 2 and 3 the following way: if the cumulative distribution function of some random variable is of type 2, and with the positive numbers as support, that is, then the cumulative distribution function of is of type I, namely. Similarly, if the cumulative distribution function of is of type 3, and with the negative numbers as support, that is, then the cumulative distribution function of is of type I, namely. Link to logic models, multinomial logic models, and certain other types of logistic regression, can be phrased as latent variable models with error variables distributed as Gumbel distributions. This phrasing is common in the theory of discrete choice models, which include logit models, probit models, and various extensions of them, and derives from the fact that the difference of two type IGEV distributed variables follows a logistic distribution, of which the logit function is the quantile function. The type IGEV distribution thus plays the same role in these logit models as the normal distribution does in the corresponding probit models. Properties: the cumulative distribution function of the generalized extreme value distribution solves the stability postulate equation. The generalized extreme value distribution is a special case of a max stable distribution, and is a transformation of a minute stable distribution. Related distributions: if then, if then, if then, if then, if then, if and then, if and then. See also, Fréchet and Weibull theorem, generalized Pareto distribution, notes. References: Imbretz, Paul. Klagenkorte Pelberg, Claudia. McCush, Thomas. Modeling Extremal Events for Insurance and Finance. Berlin, Springer Verlage, Ledbetter, M.R., Lindgren, G. and Rawlser. Copyright N. H. Extremes and Related Properties of Random Sequences and Processes. Springer Verlag. ISBN A0-387-90731-9. Rusnik, S.I. Extreme Values, Regular Variation and Point Processes. Springer Verlag. ISBN A0-387-96481-9. Coles, Stuart. An Introduction to Statistical Modeling of Extreme Values. Springer Verlag. ISBN A1-85233-459-2A.